All right, example 5, the cone. This is it, the last example of new material in all of calculus. We've made it. You guys should feel good. All right, let's do this cone example. So the idea is we've got this cone. Again, we're going to do the divergence theorem part first, and then we're going to go ahead and prove it. Using the surface integral. The surface integral on this one is messy, so I'm hoping to be able to fit it in. Again, it's not something that you have to watch. I would strongly suggest that you take a look at it because, again, you will have to verify one of these in the future. So make sure that you can do all of them by verifying, meaning do both the divergence and the surface integral. All right, I also did mention, I'm going to talk about it in this specific example. There is a way that you could technically use the divergence theorem if something is not a closed figure. So let's just assume that we were trying to find the surface integral of this, or the flux, excuse me, of this cone. But maybe the cone does not have a top to it. Well, if you use the divergence theorem, it's going to include the flux that goes through the top of this cone. So it's going to include this part right there. It's going to include that. Well, obviously what you could do is that you could take the divergence, which is going to give you the entire thing, it's the flux through the entire part of the cone, and then you could subtract off the surface integral part of the top of the top disk. So basically what you would have to do is you would have to do the divergence for the entire thing, but then you would have to do the surface integral of the top disk and subtract that away. So you could still technically use the divergence theorem on a figure like this if it wasn't a closed top. Now in this case we are going to be assuming that this is a closed top, because it does say bounded by z equals 1, which means it is a closed off top. But that is how you would use the divergence theorem if you did not have a closed figure. You would just basically have to subtract off the flux from the part of it that is not actually closed off. Alright, so let's go ahead and find the divergence. The divergence of this thing. Remember that the divergence is the partials of each component. The partial of the first component is 3x squared. And there should not be a bracket out in front of that. The partial for the second component is 3y squared. And the partial for the third component is 3z squared. Alright, so we're going to rewrite that. I'm going to take the 3 out to the front, and what I have then is x squared plus y squared plus z squared. And you might look at that and say, oh, well, let's go with spherical. And you certainly could use spherical here. I'm actually going to use cylindrical. It doesn't matter. You can do it either way, whatever way you feel like is the easiest. If you use spherical, you do have to make sure you figure out the phi part of this one, which isn't too terribly difficult. But I'm going to use cylindrical here. Alright, so we have our divergence as 3 times x squared plus y squared plus z squared, but of course the x squared plus y squared part is in polar is r squared. So this is r squared. So we know that I can write this as 3 times r squared plus z squared. And you might look at that and say, well, wait a minute, r squared and z squared are the same thing, and that is true. However, in this case, when we go to take the triple integral, r and z change at different things, so we can't actually combine those to be the same thing. If we do, we'd have to change the bounds, and I believe it would still work out. So you could try that if you want to. I'm going to do this in a slightly, probably longer way. I might go back myself and try and figure it out if I change both to r squared or both to z squared. If I use the same bounds, would it still work? But I'm not going to try that right now. So let's see. I'm going to write this in terms of polar, which I have it there. So let's see. It's going to be theta goes from 0 to 2 pi. R is going to go from 0 to 1, and that's because if I plug 1 in for z, I get x squared plus y squared equals 1. And z is going to go, as you can see in the cone there, z goes from the lateral face of the cone up to the top. So I know it's going to go up to 1, but the lateral face of the cone is going to be r. And I get that because of this piece right here. It tells me that z squared equals r squared, so I know that z equals r. That's where it starts. So I know that that's going to go from r to 1. And there you can clearly see that z and r vary from different bounds. So parameterizing that, we already did that. So it's 3r squared plus z squared. And then we did put this into terms of a polar, so we have to add the extra r, dz, dr, d theta. Alright, so we can take the 3 out to the front, make things a little bit easier on us. Then we're going to have the integral of 0 to 2 pi, integral 0 to 1, and the first one we have to do is with respect to z. So I'm going to do a couple of steps here. I'm going to distribute the r through, and then I'm also going to take the antiderivative with respect to z. So distributing the r through is going to give me an r cubed. When I take the antiderivative with respect to z, that'll be r cubed z. Distributing the z to the second part is rz squared, but when I take the antiderivative of that, it'll be 1/3 rz cubed. And we'll evaluate that from r to 1. Don't forget the extra dr d theta here on the end. I'm trying to conserve as much room as I can for the proof of this one. Let's see. Okay, so now we're going to have to plug 1 in. If we plug 1 in for z, we're going to get r cubed. If we plug 1 in for the z in the second part, we're going to get plus 1/3 r. And then if we subtract when we plug r in, if we plug r in for the first z, we get r to the 4th. If we plug r into the second z, we get plus 1/3 r to the 4th. We'll be able to combine that here. dr d theta, r still goes from 0 to 1, theta goes from 0 to 2 pi. At this point, since all we have left are r's and there's no theta, we can separate out that d theta. Oop, don't forget, don't want to lose my 3 out in the front. That'll make a big problem. So now we're going to have 3 integral 0 to 2 pi of d theta, we know what that one is, times integral from 0 to 1 of, let's see, r cubed plus 1/3 r, and then this piece right here is just going to be 4/3. Oops, that should be minus. I'll fix that in a second. R to the 4th dr. Let's go ahead and fix that. That should actually be a minus in between there. Oops. There we go, minus. Alright, so now we know this part right here is just going to be 3 times 2 pi, so we're going to get 6 pi out of that. And then we're going to have to take the antiderivatives here, so that's going to be 1/4 r to the 4th plus 1/6 r squared minus, let's see, this is going to be an r to the 5th, dividing by 5 is going to give us 4/15 r to the 5th, 0 to 1. So let's see what we get out of this. 6 pi. Plugging in a 1, you're just going to get a 4th plus a 6th minus 4/15. Plugging in 0 gives us nothing, so we're going to have to get common denominators here, or maybe I can multiply that 6 pi through and maybe simplify some things. Maybe easier to do it that way. Yeah, let's multiply the 6 pi through. So if we multiply the 6 pi through, 6 pi over 4 is going to be 3 pi halves. So we get 3 pi halves plus pi minus, that's going to be, what is that, 24 over 15, but 3 goes into both of those, so it's 8 over 5 minus 8/5. Well, that's going to be a little bit easier because I know that everything's in terms of tenths here. So that's going to be, the first one in terms of tenths is going to be 15 pi tenths minus 10 pi tenths minus, oops, I lost my pi there on top of the third one, minus 16 pi tenths, and that should not have been minus, that should have been plus there, right? So we're going to get 25 pi tenths minus 16 pi tenths, so it looks like 9 pi tenths. And believe it or not, that was the easier way to do it. Alright, that was your divergence. That's the flux through that cone using the divergence theorem. Let's go ahead and work this thing out. Now the easy part is going to be the top. That's the disk. That won't be a problem. We're going to take a couple of little shortcuts there with the disk part of it. Let's go ahead and do something different. Let's do a purple here. So we're going to do the top. I'm going to use polar as a disk. So x equals r, cosine theta. Y equals r sine theta. And in this case, z is just going to equal 1. That's the top disk. So let's go ahead and parameterize it. Do our partials. So r sub r is going to be cosine theta, sine theta, 0. R sub theta is going to be, let's see, what is that going to be? Negative r sine theta, r cosine theta, and 0. Alright, so the nice thing is, when I do the cross product, now remember we want that z component to be a positive of some kind. It should be pointing upwards. So if I do the cross product, eliminating the I row and column gives us 0. Eliminating the j row and column also gives us 0. And then eliminating the k row and column is going to give us r cosine squared minus r sine squared. So it's going to be r cosine squared plus r sine squared. Factoring out the r, you just end up with r. This is nice because the first two components of our cross product of our normal, and this is good by the way, it points up, our normal are 0. So when I go ahead and parameterize f, I could plug in r cosine into x, r sine into y. I don't care about that because it's going to get dotted with 0 for those first two components. The z component I do care about, but z here is 1, so 1 cubed is 1. This makes our dot product really nice. So let's go ahead and we'll finish this one off pretty quickly, I would think. We're going to double integrate r, because that's the dot product. I don't need to put this an extra r in there because I've already parameterized it in terms of polar, so it's just going to be dr d theta. R here is going to go from 0 to 1, and theta goes from 0 to 2 pi. So we're going to have 0 to 2 pi d theta times 0 to 1 r dr. We've done 0 to 2 pi so many times, it should become habit. That's just 2 pi. This is going to be 1/2 r squared from 0 to 1. Plugging a 1 in there, you just get a half. Plugging a 0 in there, we get nothing, so we get pi out of this one. We know the answer is supposed to be 9 pi tenths, so that tells me that the lateral face of this cone here should be negative pi tenths if we work this whole thing out right. This lateral face is kind of the messy one. So let's go ahead and start the lateral face. The lateral face or lateral side or however you want to say it. Again, I'm going to use the same parameters. X equals r cosine theta, y equals r sine theta. And in this case, because z is not just a constant, z once again from the top is r. That's what z is in terms of r and theta. So let's go ahead and figure this thing out. R sub r is going to be cosine theta sine theta 1. Slightly different than what we had before. R sub theta is negative r sine theta, r cosine theta, 0. Alright, this one will give us something different for our cross. So r sub r cross r sub theta. Crossing or getting rid of the I row and column is going to give us 0 minus r cosine theta. So minus r cosine theta. Getting rid of the middle row and column is going to give us 0 minus minus, so it's plus r sine theta, but we have to change the sign to negative r sine theta. And getting rid of the k row and column is going to give us r cosine plus r sine, so we know that that's r. This is actually not good. Let's go ahead and take a look at the cone and see why. Remember, we want this thing to have outward flux. Well, if r is positive, this thing is not going this direction. That's a negative r value. We need it to be going down. The z needs to be in a downward motion. So we know that our normal is going to be incorrect. But that's easy to fix. We're just going to literally change our normal by switching everything. So we know it's going to be r cosine, r sine, and then negative r. It just means we switched the cross, that's all. So there's our normal. We do need to parameterize this one. We don't really have a choice. So it was x squared, y squared, z squared. So x squared, all cubes, so it's r cubed cosine cubed theta, r cubed sine cubed theta, and r cubed. All right, now we have to dot these. This is where it starts to get really messy here. So I know I'm going to have a double integral. Okay, r still goes from 0 to 1. Theta still goes from 0 to pi. Okay, I've gone ahead and parameterized these things in polar. We won't need an extra r, which is good. So we're going to have, dotting these, we're going to have r to the fourth cosine to the fourth of theta plus r to the fourth sine to the fourth of theta minus r to the fourth dr d theta. The nice thing is we still can separate the r's and the thetas because I have r to the fourth in common. I can pull the r to the fourth out. So we are going to have an integral from 0 to 1 of r to the fourth dr. Believe it or not, that will be the much easier part. Then we're going to have this integral from 0 to 2 pi of cosine to the fourth theta plus sine to the fourth theta minus 1. Don't forget that minus 1 when you factor the r to the fourth out, d theta. This first part will be easy. That's just 1/5 r to the fifth from 0 to 1. So we know we're going to get a fifth there. That is by far the easiest part of this thing. Good, I left myself plenty of room. Down here on the bottom, I'm going to go ahead and break down the cosine to the fourth and the sine to the fourth. This is where things get really messy. So cosine to the fourth theta is the same thing as cosine squared theta squared, which means I can break that down to be 1/2, using the reduction, 1/2 of 1 plus cosine of 2 theta, that whole thing squared. So when I square that, I'm actually going to get a 1/4. I have to FOIL this piece, so it'll be 1 plus 2 cosine of 2 theta plus cosine squared of 2 theta. All right. The sine is going to break down basically the same way. So sine to the fourth theta is the same thing as sine squared theta squared, which is, by using the by using the reduction formula, it's 1/2 1 minus cosine of 2 theta, that whole thing squared. And again, when I square this thing, I'm going to have to FOIL this piece right here. So I know I'm going to get 1/4, and then FOILing is going to give me 1 minus 2 cosine of 2 theta. And again, minus times minus is plus, so it's plus cosine squared of theta. Okay, I have to add these two things together. So I'm going to kind of create a little bit of separation here. I think that should give me enough room. Let's hope so. So I got to add these two pieces together. All right, so let's see here. If I was to distribute, I'm going to get 1/4 by distributing that to here, 1/4 by distributing that to there. Adding a fourth and a fourth gives me a 1/2. Here, I'm going to get a 1/4 times 2 cosine of 2 theta. Here I'm going to get a fourth times negative 2 cosine 2 theta. Those things are going to go away. Those are going to subtract out. And then here we're going to get 1/4 of cosine squared. Here we're going to get a fourth of cosine squared. So we're really going to get plus 1/2 cosine squared of 2 theta. I still have to break down the cosine squared once more. So really what I'm going to get there is I still got a half. Got a half from this one. And then breaking down this cosine squared of 2 theta right here is going to be 1/2 1 plus cosine of double the angle, so it's 4 theta. So let's see here. Distributing everything, I'm going to get a half plus 1/4. That's distributing this into here. And then I'm also going to get a fourth cosine 4 theta. So out of all of that, I'm going to get a half plus a fourth, which is 3/4, plus 1/4 cosine 4 theta. Okay, the only other thing I have is I have to subtract the 1, but I'll go ahead and do that in a second. So let's go ahead and plug that back in. So now I've got the integral from 0 to 2 pi. This piece right here, we just found down here, that's 3/4 plus 1/4 cosine of 4 theta minus that 1 that was still up there. So I'm going to go ahead and combine the 3/4 and the minus 1, which gives me a negative 1/4 plus 1/4 cosine 4 theta d theta. Whoops. Bring down my 1/5. Alright, so now we can take antiderivatives after all of that. So we're going to have negative 1/4 theta. Let's see, plus 1/16 sine of 4 theta from 0 to 2 pi. Well, the good thing is if I plug 2 pi in, 1/5 there, if I plug 2 pi in, I'm going to get negative, let's see, 2 pi is going to be negative pi halves. Plugging 2 pi into here is going to give me sine of 8 pi. That's 0. Plugging 0 into both of these is going to give me 0. So I get 1/5 times negative pi halves, which is negative pi tenths. And when I add pi plus negative pi tenths, we get 9 pi tenths. And there you have it. That is the end of Calculus 3.